Hello students, welcome to my YouTube channel Data Sharp. Today we'll be talking about graphical method. In the last lecture we have studied about the formulation of the linear programming problem. So now we'll be discussing about the graphical method. So graphical solution, as we can it's very easy to relate that we are talking about graphs. So here we'll be talking about a 2D graph. So it has a x-axis and a y-axis. So it is limited to a linear programming models containing only two decision variables. It can be used with the three variables, but that would be with great difficulty. So that would be a 2D graph, x and y graph. Graphical methods provide visualization of how a solution for a linear programming problem is obtained. So whether it's a minimization type or a maximization type, we can find the optimal solution of our problem. So consider the same example that we have taken in the last lecture that was related to the moles and the mugs, and you have to find out the number of moles and mugs so that you can maximize your revenue. So we have the objective function, if you remember. So I'll quickly write down the objective function: maximize z, that's 40 x1. x1 is the number of bowls to produce, plus 50 x2. x2 is the number of mugs to produce, subject to the constraints. So here we are talking about the labor constraint first. So it would be 1 multiplied by x1, 2 multiplied by x2, less than equals to, we have 40 hours of labor. And the second one for the clay, so this would be 4 times x1 plus 3 times x2 less than equals to 120 pounds is the maximum limit, where x1 and x2 is greater than equal to 0. So we have formulated this linear programming problem in the previous lecture. So continuing with this, how I can now be presenting it graphically. So whenever we have to represent our LPP graphically, so we'll be plotting our constraints over the graph. So before that, let us consider what is a feasible solution. Feasible solution means that that particular solution that doesn't violate any of the constraints. So the constraints that we have, like in the previous one, we have 3 constraints, as you could see. These are the 2, and this is the non-negativity constraint. So we have 3 constraints. So if none of them is violated, then it is called a feasible solution. So here you can see, if I take x1 and x2 as 5 and 10 respectively, then both of them are greater than equal to 0, strictly greater than 0, I'll say, and they are satisfying the labor constraint and the clay constraint. So that means it's a feasible solution. On the contrary, if it violates any of the constraints, then it becomes an infeasible solution. So here you will see that both of them are greater than 0, strictly greater than 0, but the labor constraint is violated. It is greater than 40, whereas when we see this, so this would be 80 and 30, that's 110, that's less than 120 pounds lbs, right? So even if one of the constraints is violated, so we have an infeasible solution. So now consider the example, the number of bowls and the mugs one. So I'll represent the bowls, that is x1 on the x-axis, and mugs x2 on the y-axis. So here you can see we have labeled them. So we have a scale of 10 each on both x and y-axis. So representing the linear constraints on this graph would be, we are talking about these 2 constraints. Now we'll be plotting the line, that is the first one, that we have x1 plus 2x2 is less than equals to 40. So first of all, we'll plot the line x1 plus 2x2 is equal to 40. So you can just quickly, because it's a line, so we can calculate the 2 points through which we can draw the line. So when x1 is 0, we can see that x2 is coming out to be 20, and when x2 is 0, x1 is coming out to be 40. So using these 2 points, here we can see this is 40, 0 and this is 0, 20. With these 2 points I can draw the line, and less than equals to 40 means that we are talking about, if this is my line, this is the region that I have to shade, less than equals to 40. So below this line, so this is blue shaded region, you can see that's the label constraint area. Now we talk about the clay constraint area. So as it is 4x1 plus 3x2 is equal to 120. So again I'll create a box where x1 is 0 and when x2 is 0. So when x1 is 0, I can formulate that x2 is coming out to be 40, and when x2 is 0, it is coming out to be 30. So here you will see at 30, 0 and 0, 40, I can draw, with these 2 points I can draw the line. Again, it is less than equals to 120. So when you will draw a line, we'll mark it like this, that it's the shaded area is lying below this. So this blue shaded area is the clay constraint area. Now this is just separate to make you understand, but when you will be doing it in your exam, you will be plotting only one graph and both the lines would be there on single graph. So here you would see that this is your 4x1, sorry. So 4x1 plus 3x2 less than equals to 120, and this one is x1 plus 2x2 less than equals to 40. Yes. So now we can see the common region. The common region, that is the shaded region which is common to both the constrained areas. So we are getting this point. So now what we have to find out, we have to find out the extreme points. So these extreme points, because this all, that is the shaded region, is our feasible region. So all the points that you can see in this shaded area are the feasible solutions, but we have to find out the optimal solution. So optimal solution can be found only on the extreme points. So we have to calculate these points. So let me take this as O. O is 0, 0. This is A, 0, 20, B, and this is C, 30, 0. So how we can find out B, the point? You can just find the intersecting point of these two lines. So just put x1 as 40 minus 2x2 in this equation. So this would be 4 times 40 minus 2x2 plus 3x2 is equal to 120. So that's 160 minus 8 plus 3. So 40 is equal to 5x2. So x2 is coming out to be 8. So x2 is 8. And what about x1? So it would be, x1 would be 40 minus 8 2s are 16. So we are getting it as 24. So here you can see we are finding out the points. Now what we have to do, we have to find out the objective function, at which point we are maximizing the objective function. So we can easily find that the objective function is maximum at this point B, because we are getting the maximum profit as 1360. At this it would be 0 only, Z would be equal to 0. At this is 1000, 1200. So the maximum profit we are getting when we are producing 24 bowls and 8 mugs. So this is how we can find out the solution. So let us consider another example. In this again, it's of maximization type, and we have the 3 constraints plus the non-negativity constraint. So what we'll be doing, so the first and the foremost step is you will be plotting the lines x1 equal to 6, 2x1 plus 3x2 equal to 19, x1 plus x2 equal to 8. So just x1 equal to 6, as we know, it's a line parallel to the x2. So this is how we will be getting x1 less than equals to 6, means we are talking about this area. So the whole region would be shaded, right? So next is 2x1 plus 3x2 less than equals to 90. So you can calculate the 2 points like I have told you before, and less than equal to this. So this is the shaded region. Now x1 plus x2 less than equals to 8, again these are the 2 points through which we can draw this line, and this is the shaded region. Now what we'll be doing, all these 3 lines separately I have just shown. So I'll be plotting in one graph only, and then I'll be marking the common shaded region for all the 3 lines. So what you can see, this is x1 less than equals to 6, this was x1 plus x2 less than equals to 8, and this was 2x1 plus 3x2 less than equals to 19, yeah. So now again the corner points, extreme points will give you the optimal solution. So let this be O 0, 0, this be A 0, 6, B we'll find out, C we'll find out, and the point D, that is 6, 0. So C would be as you can see here in this line, this is equation number 1, 2, and equation number 1, when x1 is equal to 6, so 1 implies x1 is 6, so we can calculate the value of x2 as 2. So this would be 2, 6. Now in the second B point, to calculate B point we have to find out the intersection of 2 and 1. So the another way of finding the values, you can just 2 can be written like this only, and I can multiply 1 by 2. So this would be, and subtract them. So x2 is equal to 3, and if x2 is equal to 3, so x1 would be 8 minus 3, that is 5. So again I'll get the point as 5, 3. So you can easily locate that we are getting this point only 5, 3, and this is 2, 6. So now I have got the extreme points. So what's the task? The task is to find out the maximal our optimal solution, at which point I am getting it. So here you can see that we can separately find out at O, A, B, C, D, and I am getting the optimal solution at x1 is equal to 5 and x2 is equal to 3 as 46. So you can just put the values and we can get the answer. So quick summary, that whenever we are doing the graphical solution for the maximization problems, you have to find out the feasible solution for each of the constraints. So determine the feasible region that satisfies all the constraints simultaneously. Move any feasible solution on the objective function line with the largest value is the optimal solution. Moreover, the extreme points that I told you, the corners of the feasible region, would be giving you the optimal solution at last. So the optimal solution can be found at the extreme point of the feasible region, and all the solutions that is inside the feasible region is generally feasible solution points only. So let's consider the next example of the minimization type. Here you can see for the minimization we have the greater than equal to. So quickly I'll just show you that In this we have the minimize 5x1 plus 2x2. So plotting all these lines again, you have to plot all the lines using the same method. So this would be 0 comma 4 and this is 4 comma 0. So just plot the line x1 plus x2 equal to 4. So 2x1 plus 5x2 is equal to 10 would be 5 comma 0 and 0 comma 2. So you can see the line. Then at last we have 4x1 minus x2 greater than equal to 12. So you can plot this line as well. So you will see that when x1 is equal to 0, x2 is equal to 12. So x2 would be 12. So we'll be plotting it, and x1 is equal to 3. So we can plot it. Now in this case, when we are talking about the greater than equal to, so we will see that we are talking about these regions, right? So this is the common region, but we want to find out the minimum of this. So the minimum would be at this point. So the optimal solution can be obtained at x1 16 over 5 and x2 4 over 5. So we can easily find the minimum of the z. So consider this question where we'll be talking about the unbounded solution. So this is a maximization type question, and in this we have the constraint of greater than equal to. So here when you will plot it, we'll see that 3x1 plus x2 is greater than equal to 8. So we are talking about this region. x1 plus x2 greater than equal to 5, again this region. So the common region would be this only. So this is what we are having, right? But as it's a maximization type, the objective function, so we cannot find the maximum of the objective function, as it is in going up till infinity, right? So z is increasing because x1 and x2, it doesn't have a bound. So therefore we are having the feasible region as unbounded, and the solution is also unbounded. In this question, we are talking about the infeasible solution. So maximize z, that is 2x1 plus 6x2, subject to the constraints where it is of one is less than equal to type and the another is greater than equal to. So when you will be plotting these two lines, so what we will see that we are not able to find out any common region. So if there is no feasible region, any common region between the lines, so how would we find the optimal solution? We won't be able to find the region. So it's an example for the infeasible solution. So here it is greater than equal to 8 and this is less than equals to 12. So can we see any common region between these two? No, there is no common region. So this is, we are getting infeasible solution. So this is it, and in the next lecture we'll be talking about the canonical form of the linear programming problem. Thank you so much.